So in traditional programming, we have some input and a program. We give it to the computer and it will calculate some output for us. But when doing machine learning, we have samples of inputs and the desired outputs. And then we want the computer to find a program that finds the relationship between them. So here we want to learn just from data. We have some algorithms, but they work with many different tasks. They could do face recognition, they could predict the weather, a lot of stuff. So they are not specific to your task, but it will learn how to do that task very well with given data. We have three classes of machine learning methods: supervised, unsupervised, and semi-supervised. In supervised machine learning, it's like teaching something in a course. You give it some samples, so the professor teaches you something, it gives you sample questions, but they will take an exam which has similar questions, which has the same stuff that has been given to you throughout the course. So this would be something called supervised learning. You have the data and you have the desired output. The computer will learn the pattern between going from the input to the desired output. We have unsupervised learning, which means we have a bunch of data, but we do not know what the desired output of this program would be. An example could be classifying users of Facebooks into 10 groups to show them ads. We could have a program that automatically creates 10 groups and places people who are similar in those groups. So we do not know exactly what will our groups be. It will find 10 groups that work pretty similar to each other, and we could use that to show them ads and find good ads for different groups of people. It could find out that people who check their Facebook accounts frequently will be put in one group, the younger people will be put in another group, so the ads that will be shown to them will be different. And we also have semi-supervised machine learning, in which we have a lot of data that we do not know the desired output for, but we have a small amount of data that we will label them ourselves. The example would be Google Photos. If you have used it, it will recognize different people in your images and it will group them together, and then it shows you one picture of a person. Who is this? You say, okay, that's my mom. And it will learn how your mom looks in different images, and it will classify it based on that for later on. We have two different problems in machine learning. One of them is classification, the other one is regression. In classification, we have some discrete groups. Is tomorrow going to rain or not? 0 or 1. Is this ad good for this person or not? These are classification problems. But sometimes we want to predict the value of something. So for example, what is the price of this house? It is not, we could do something like classification with it. Is it below $100,000 or above $1 million, or classes like this? But we could also do something called regression, which means try to predict the value, and it will predict, for example, $434,000.75. It can create a real value for you. So let's go to the Jupyter Notebook for this section. We are going to use a couple of libraries here. As I said, NumPy is a great library for interacting with matrices and creating them, doing matrix manipulations and multiplications and stuff like that. We also have a library called Matplotlib. It is a plotting library that looks like what you are used to in MATLAB. So the name is has math there because it's like MATLAB. So In MATLAB you do plot x comma y. Here you do matplotlib dot plot x comma y, just like that, and it will work similar to what people are used to in MATLAB. We have a library called Pandas. Pandas is a great library for loading the dataset, writing to a CSV or JSON file, and creating subsets of datasets, stuff like that. So you could connect any source of data to Pandas. You could just connect a MySQL database to it, or read a CSV file or any kind of information data that you have. You can load it up inside Pandas. And we're going to use it to load CSVs and create a subsection of them and stuff like that. There's also a library called scikit-learn, sklearn. This is the most popular machine learning module in Python. So it has a ton of algorithms inside it. It has all sorts of algorithms that do regression or classification. So it can be a very nice library for you to use. So first of all, in this first section, I'm going to write the version of each of them so that later on you can see what versions I had installed on my laptop when I run this code. So we are going to do a classification task for the iris dataset. So the iris dataset is for finding out which plant this is based on some features, but actually I have no idea how they measure those features. But it has something like sepal length or wreath or petal length. And based on those, it will the machine learning should try to classify which kind of flower we are dealing with there. So first of all, we have to load the dataset, import all the libraries. Usually you would do this incrementally, so you would first import pandas and then see, okay, I now need something to, for example, create a scatter matrix. So you can search this online, find out that it's inside pandas.plotting. So you could do from pandas.plotting, import a scatter matrix, and then go ahead and use it later on. So usually the way you go with it is going incrementally, but it's already done here, so I'm just gonna execute it. So for loading the dataset, I will be using this GitHub URL. So this is a CSV. It has my features there, and in the end we have the class that we want to classify them into. And you see that there are 3 different classes here. So I could just feed this URL into pandas. It has a function called read CSV. And you could easily look at other functions it has using Jupyter Notebook. Here I just write pandas.read underline and press tab. And it should, it loads up a bunch of read functions from pandas. So you can see that I could read from clipboard, I could read from CSV, Excel, HTML, JSON, any kind of format that is listed here. You could also connect it to databases to do machine learning with very large amount of data. It can also be connected to Google BigQuery. So we did a project a while ago in which we used 480 gigabytes of data, which was the whole Stack Overflow. So in Google BigQuery, each query will take less than a second for you. So it will be very nice to have in large amount of data.
Can you upload that whole CSV file?
Yeah, you can upload anything to Google BigQuery. Yeah. Yeah, you upload it to Google BigQuery, and then you get the URL from them. You can input it here, and pandas will load from that. And any part of the library you want to query, it will automatically get it from BigQuery. You could also use the BigQuery module in Python, which gives you a pandas dataset to work with. So you can just get a subsection of it and it will automatically query and get the results back to you. So these are the names of the columns that we are going to use: sepal length, sepal width, and I just specified this URL. So it will get this from here. We have in pandas, so let me show you, print type of this object that we call dataset. It is a pandas core data frame. So data frame is like a 2D matrix in pandas. If you fetch, for example, one column, it will be a 1D, one-dimensional matrix, which it would call pandas data series. So data series is one-dimensional, but data frame is two-dimensional. You have different columns and rows. So it has a function called head. Head will, by default, grab the top 5 rows from your dataset. So here we have 5.1 and then 4.9. As you can see, it is grabbing those and writing them here. I could also pass a number here. I could have the top 7 rows in that dataset and it will fetch it like this. So here you see how working with Jupyter Notebook is pleasant for doing machine learning. As you can see, this dataset that is loaded here can be shown pretty nicely inside here, and it highlights the rows for me, so I can work with them, find the data in there pretty easily. So the next step would be summarizing the dataset. So it has a property called shape, which gives us the shape of that dataset. It is a 150 row by 5 columns dataset. We could take a look at the data. Here I passed 20, which means print out and fetch me the top 20 rows in that dataset. I could get a statistical summary of these. So this is the count, mean, standard deviation, minimum, maximum, and quartiles there. So you could take a look at different features, see what their minimum and maximum values are. So you might have to do something if one of them is much larger than the other. But I'm not going to talk about that here. If you want to know more about what you need to do about scaling your different columns and stuff like that, take a look at the book that I have added the URL to inside the repository. We could take a look at the distribution of different classes. So as I said, some of these are iris setosa, some of these are versicolors or stuff like that. It will say that each of these has exactly 50 rows that is labeled with iris setosa or any other label. We could do data visualization. So we could have box plots here, and we could also do histograms. So the syntax is pretty easy. It is just writing the name of the dataset and say .hist, call this function. If I don't pass a specific figure size, it will look like this, but I want it to be a bit larger so you can see it easily. So I pass the figure size to it and it shows up like this. You could also have a scatter matrix, which is in its main diagonal. It will be histograms, and then here it is scatter matrix, scatter plots. So it's basically pointing all the dots are different data that we have in our data sets. So the way it goes with supervised machine learning is usually you have a data set, and for each row you have a specific answer to it. So for example, if it's facial recognition, you have an image and you have the name of that person assigned to it. If it is something like we have here, you have a set of variables that you have measured, and you have a class of flower that you want it to learn, and you want to be able to give it a measurement, and it will say this is this kind of flower, or answer that and predict that for you. So the way it goes is usually you split your data set in 2 or 3 parts. If it's 2 parts, it will be a training set and a testing set. So this would be sample questions throughout, for example, a course, and then the test set will be an exam. You want to know how good and accurate your model is based on how it does with test set. So you show it the training set, and then try it out on the test set, evaluate the results, and see the accuracy. And say, for example, this got 90% of questions right, so the accuracy of this method is 90%. So what we want to do is doing train test split. So this here says that the validation size that I have set here is 0.3. So this means that I want the test size to be 30% of my data, and the rest 70% will be my training set. So we are going, if you run this, we have xtrain, xtest, ytrain, ytest. So whenever I want to do it, I just do this tab autocomplete and then do shift tab, bring up the help for this function. I can open it up here. And you see that it has a docstring, says what parameters it needs. And if you go further down, you see examples of how you should use it. So this is pretty nice. I could just say, copy this part, xtrain, xtest, ytrain, ytest equals train test split, x and y, test size, and some random states. This random state will make your code reproducible, so if you run it multiple times, it will give you the same values. But if you don't give it, it will be random every time you run it. So this is just like the example there, xtrain, xtest, ytrain, and ytest. So I can see their shape. One of them has 105 rows, another one has 45 rows. So this is like 30%, 70% split of my data. So what I should do is I should show the training set to my algorithm and then try it out on the test set and see how well it did. So I will get back to this later on, but imagine you want to use the linear discriminant analysis algorithm. This is one of the most famous classical machine learning algorithms. It's a bit old, but still works pretty good. So the way you go about it is you first search for sklearn and then linear discriminant analysis. And then we can go to the help of this function. So it is inside sklearn.discriminant analysis. So if I want to import this, I will have to write from sklearn.discriminant analysis import linear discriminant analysis. I want this object imported from that module. Okay, so is everyone okay with this? Because loading a lot of libraries in machine learning could be hard to do. So if you want to go further, you have to learn how to load different parts of a library pretty easily. Okay. So here we say LDA equals, after importing the linear discriminant analysis, which is done here from sklearn.discriminant analysis, import this. Here you just call that object dot feed the training set X, which is the features that you have measured in your training set, and the training set Y, which is the label, the answer that you want your algorithm to be able to predict later on. So if this was weather, this would be my measurements, for example, the velocity of air or stuff like that. And then Y would be the weather that they resulted in. So for example, if it's sunny, the Y would be sunny. If it's rainy, Y would be rainy. So here Y is the class of that flower that we want to classify, and the X are the measurements that we have done. So we call LDA.fit, which means try to fit your algorithm to this specific data. And then it can do predictions. So you would do LDA.predict and then give it the test questions. X would be questions. You get their predictions, which is their answers to those questions, and then you check those answers with the key for that exam. So the key would be y-test. So here I calculate the accuracy score from predictions and y-test, and it says 0.97, which means this algorithm has an accuracy of 97.7% on this dataset. We have something else called confusion matrix. Where are the places that it had a mistake? So here the left will be the actual values, and the top would be the predicted values from our dataset, from our algorithm. So you see that we had 12 values for the first class, and we got all of them right. But some of our predictions did not match the value. So in this case, we had exactly one mistake. So since we had one mistake, and the size of our training set was, let's find out the train test split. Yeah, it was 45. Our accuracy would be 44 out of 45, which is 97%. So this is usually useful for debugging. For example, a while back I was doing face recognition, and the accuracy was pretty low. And after looking at confusion matrix, we found out that we had two folders that had the same name. So the same name was assigned to them, so it was creating a mistake between them. The same guy's pictures were inside them, so it was creating some mistakes, but it was due to the problem with our dataset. So fixing the dataset would fix the problem. So it's usually for debugging, but most of the time, if you're using a well-established dataset, you can just go with accuracy score. It also gives you classification report, which gives you some stuff like precision, recall, and F1 score. So precision is basically if I say this is from class A, how reliable am I? So if there are, for example, 100 class A instances in the data set, and anytime that I say class A, it is right, my precision would be 100%. So I don't think that was pretty clear. So precision is if I say it is from class A, how much of the time would I be right? So if I'm saying class A all the time, I would be wrong for most of it. But whenever I say class A, if it's right, then my precision would be very high. But we have something called recall. How much of class A's that are in this data set am I going to capture? So imagine we want to find out theft. Precision would be if I say this is a theft, how much of the time would I be right? Recall will be out of all the thefts that are happening, how much of them are we capturing? I might have a very high precision, which means I capture a couple of those. So anytime I say theft, this is like 100% a theft. But my recall could be low, which means that I'm letting like half of them go through without catching them. So you see that you just have to instantiate that object, call the function feed, give it the training data, call the prediction. After getting its results, you could just evaluate those predictions and see their accuracy. And based on that, you could tune your parameters or find a better algorithm for that task. For example, for this specific task, we could just call these 3 lines of code for different algorithms. For example, logistic regression, linear discriminant analysis, k-nearest neighbors. These are all famous machine learning algorithms. And I could just run it for all of them and see their accuracies. And here, as you can see, LDA does the best among those. So this way I would know that LDA is the best choice for me now, and I would choose it and go along with it. And we could also try to plot those results. So here we can see that this one has a better accuracy, which is LDA. Okay, that's all. As I said, this is very introductory. So if you want to continue learning about each of these subjects, you can go ahead to the GitHub repository. There are like 20-30 links there, and I have specified 2 very good sources of books that are good in this area. One of them would be A Bite of Python for learning Python, and the other would be Introduction to Machine Learning with Scikit-learn. And that is a O'Reilly book that has a lot of examples and has the most well-known machine learning algorithms in there as well. Okay, thank you.